Hello, my name is Jun Kim, and I will present our work called Hydra. As network gets bigger, faster, and more complex, it is harder for human operators to make them work correctly. One glimmer of hope is that the networks are becoming increasingly programmed top-down, meaning that their network-wide behavior is established at the control level and then compiled down to rules running on switches and NICs. This lets us dictate network-wide behaviors without needing to know how each individual element operates. At the same time, networks are becoming programmable end-to-end, meaning the end-host stack, smart NIC, and switches can be programmed using languages such as P4, eBPF, and DPTK. What if we could tie this all together into a closed-loop system, in which we determine behavior at the top level, then check that individual packets are being processed correctly at the bottom, in real time, then feeding it back to the control system for corrected behavior. Just imagine, networks could, for the first time, be controlled and run automatically. Not just by randomly catching errors with pings and trace routes, but by immediately and reliably stopping errors in their tracks without human intervention. Networks will be more reliable and trustworthy, and operators will feel more confident about trying more daring ideas, which, after all, was the original rallying cry of SDN. So what are these problems we are trying to catch? For sure, we need to catch the familiar set of errors that are caught by static checking, including loops, black holes, and reachability problems. In addition, we need to catch errors that static checking can't catch. Runtime errors caused by bugs in the implementation, and hardware failures such as bit flips or noises on buses and serial links. For example, consider a network in which a packet header field indicates which packet belongs to which tenant. In this example, we want to make sure a cat tenant and a dog tenant cannot send packets to each other. But if this bit is flipped by a hardware failure, a packet might show up in the other tenant's network, which would be a disaster. We are going to make a radical and ambitious goal to try to catch errors in real time immediately so that such packets cannot make progress and drop them in their tracks. And this means adding tests in the data plane to execute at line rate during runtime. There are some practical challenges to overcome. How can we express the errors we are looking for in the data plane? And how can we add this complexity in the switches and NICs without too much overhead, slowing them down or making them even more complex? And third, how do we make it simple to express the failures we are looking for so that network operators can write the checks themselves? We came up with a solution that works for any network, whether it's truly programmable or not. It is scalable and works in real time, paving a way to closed-loop control in the future. We call our system Hydra, and I'm going to start by giving you an example of how it works. I'll start with a trivially simple warm-up example. Let's revisit the example with the cats and dog tenants. Many virtual and slice networks use a packet header field to indicate which tenant or slice a packet belongs to. If a single bit is flipped, it can be a disaster. We can check for it with a static checkers to make sure the forwarding rules are installed correctly. And we should. But if the implementation is wrong, for example, a bit is flipped in the memory, we won't catch it. Here's a description of the hardware checker written in our language called Indus. Notice that the code is really easy to read. It has three parts. Init, which runs when the packet enters the network. Telemetry, which adds state to the packets as they pass through the switch or smart NIC. And a checker, which runs checking code only when the packet exits the network. All Indus programs have these three parts. Next, a compiler turns the code into P4 code running on each switch or smart NIC, alongside and isolated from the forwarding code. Notice that the runtime verification program is a top-level specification that we write once for the whole network, not for each switch or smart NIC. The program compiles down to P4 right now, but could compile down to multiple different targets. Because the checking code runs at line rate in real time, it can check and act immediately on every packet. Let me talk a bit more about the Indus language. Indus programs can access control and data plane state. Control plane states can be accessed through control variables. These are states configured by the control plane. The telemetry variable carries information of the packet through the network, which is checked at the last hop against the control plane dictionary again. And Indus programs also allow a checker to maintain state across packets to manage flow state. We call these state variables sensors. Please find more about this in our paper. Indus makes sure that our checker code does not interfere and mess up with the porting state running on the same device by maintaining a strong isolation. This is largely done by Indus strong typing. For example, the control and header bits are strictly read-only in the Indus language. As a demonstration that Hydra works in the real world, we applied it to Ether, an open-source cellular platform. Ether implements network slicing using a service called application filtering. For example, we might specify that a set of cameras can only communicate with a video analytics service, but not with the internet. I won't go into too much detail, but the issue arises because Ether had to implement this functionality across 2 tables to optimize the ASIC resource usage. Unfortunately, a bug in the control logic that maps commands down to these tables led to a bug where the combination of these 2 tables would execute the wrong action on certain packets. Using the Hydra program, it was easy to detect this bug. Note that there can be cases where the bug is dropping packets that should have been forwarded, so we report them to the controller instead of rejecting them. This bug would nearly be impossible to detect with static checking. One would need to correctly model every layer in the control plane, data plane, and compiler and drivers, and that's infeasible. Whereas with Hydra, we are able to find the bug with a simple Indus program that takes less than 50 lines of code. In effect, using this small program, we are able to verify the entire behavior of the end-to-end system. Note that we are not advocating to replace or eliminate the practice of static checking. We are proposing a runtime verification as an orthogonal check that runs in the data plane. Indus is deliberately easy to write and understand. Indus is a scripting language, which is more familiar to human operators. Indus is surprisingly expressive as well. In fact, in this paper, we proved that Indus can express any network behavior that could be written in LTL or linear temporal logic. The checker program fits and runs in the data plane, thus the checks run at lane rate. And it does not add too much overhead. We implemented a variety of checks using Hydra, as shown here, and none of them added significant overhead in terms of number of stages and PHV resources. A really important outcome of our work is that the checker code can run in parallel with the forwarding code. To summarize, it's important to have techniques for ensuring that networks operate correctly. Hydra offers a new style of network verification, network-wide properties that are specified top-down and compiled into the data plane itself, operating alongside the forwarding code and stopping errant packets immediately in real time. Please check out our paper for more details, and thank you for your time.